Hello brothers, so we want to explain the code of SSA for unit commitment and economic dispatch. So the first thing is to the function will identify some parameters like initial t on, initial t off. As you see here, there is the first two generation and the other is off, and this is the initial t of time, unit outages time. So the other 8 units is off, and this is the minimum up, minimum down, and minimum up time allowed for to continuous boost time or continuous shutdown time. And this is the initial stage for each generation. As you see here, the first two generation is on in the first of this period, and the period is for 24 hours. And after that we define the power max for each generation and power minimum for each generation, and then we define the power demand for 24 hours. And after that we calculated the spinning reserve, and then we define the wind power of this file and define the velocity v, cut on, cut off, and the normal velocity and power, rated power. And after that we calculated for 24 hours the profile of wind from here. As you see here, this is profile for wind, and after that we calculated the net load that went from unit to economic dispatch and unit commitments by subtract between the load of the system minus the power from the wind. And after that we define A and B for each generation, for 8th generation, and also the conversion factor, emission factors A1, B1 and C1, and startup costs at what condition, and startup costs at cold condition. And after that we defined that when the unit is to be cold or hot. And after that, as you see here, we define the maximum iteration and the sending or descending the power maximum. That means we defined the power maximum from the maximum to the minimums, and it defines identifies some other parameters for SSA. And after that, from here we will initialize the particles, number of particles, feasible particles. These are initialized randomly. As you see here, the initial of the swarm here, the swarm initialization from the initial function, and then we calculate if the function verify, and after that we calculate that fitness or objective function, and calculated the costs of generation. As you see, we will explain deeply in this, but first we define the initial state for each generation for 24 hours. This is the function of initial. The swarm is the initial for each generation for 24 hours, and then we enter the swarm 1 to verify function to check on the load is covered by the generation, or if you the generation is more than load, or the load is more than generation. And after that we also check on the minimum upper and minimum downtime for each generation and verify that if the swarm is okay. So we put in the swarm here, but if not okay, we will make some modification. And after that the swarm uh, gets it from verify function. We put it in the objective function to calculate the fitness. And after that, after calculating the fitness for each particles or for each swarms, we now compare. As you see here, we compare between the swarms to get the best or food position and food fitness, the leader fitness and the leader position. So this is, we compare between all the particles swarms to get the best one dependent on the fitness function, that this is the particle which has the minimum fitness values, and these values will be lead all other particles in the next system. And after that, we display the best food fitness on the command windows. And after that, from here, we will start the code of SSA optimization that will be explained in the next video. This is the second video to explain the SSA optimization function for unit commitment, and after that, as you see here, we started from here by iteration dependent on the maximum iteration of the SSA optimization. The first thing is to calculate C1, C2, C3. As you see here, this is from the SSA algorithm. So the constant one dependent on the current iteration and the maximum iteration, and we calculated C1 and C2, and C3 is a random variable and random numbers. If the C3 is less than a 0.5, so the function, the new position of the swarm is the best position. We got it from the initial state plus C1 multiply C2. If the C3 is more than 0.5, the real or the position. The new position is the food position minus C1 multiplied C2, and after that we compared between the new position and random variables to get it. A new position for each generation for 24 hours. As you see here, this is after that for each generation for 24 hours. As you see here, this is the new position. Now we get the new position for swarms, and after that we, as you see here, get this swarm that we get it from here on that a verify function, as you see, to check on the minimum and maximum downtime and minimum uptime and load discovered by the generation. And after that we get the new, and after that we get this swarm and put it in the object fitness function and calculate the fitness and compare with the leader fitness. If the new fitness is less than the leaders, so this is the fitness or the swarm will be the leaders. If not, the leaders will be the same. And this is for if the iteration, as you see here, less than 15. If the iteration is more than 15, we get another function to get the new position of the follower slab. As you see here, the follower slab is 0.5 multiplied by swarm, the current swarm and the previous one. So this is, and get it, the new position for the swarm and compared with the random and get it to the X, and to get it the state for each generation for 24 hours for the new swarms. And after that we store in the swarm and put it in the verifier to get to test the feasibility of the swarms and get it. The new swarm, if we make some changes and some condition does not happen or verify, and after that we put this a swarm in the objective function and calculate the fitness and compare it with the leaders. If their fitness is less than the leaders fitness, so the new swarm is this is the leader position and the new fitness is the leader fitness. And this is a stage, this is the procedure repeated for all the swarms, and after that we calculated with the leaders with the food fitness. If the leader's fitness is this more than or less than the food fitness or food position, so the leaders will be the food position and the leader fitness will be food fitness. And after that repeated for all swarms as you see here, and then we display on the command windows, in the command windows, the best food fitness values and repeated that for maximum iteration, and that will be defined in the first of the program. And this is the finish of the iteration and the function of main function of SSA. And after that we will start with that to display the result that calculated the result that will be explained in that video. This is the third videos to explain the SSA optimization function. So after we get the value of the state of each generation for 24 hours, now we will start to calculate all the results from here. As you see here, we define some initially state type of optimization. As you see here, the type of optimization for economic dispatch, and display all of our warning or anything. And after that we initialize the fuel cost and the emission cost, and then fuel cost for 24 hours and the emission cost for 24 hours. And after that we will start to calculate the H and C and the AEQ that dependent on the state of food fitness. The H is dependent on the C factor for each generation, and that will be used in the economic dispatch, and the C also dependent on the B for each units and the state of that generation unit, and use it in the economic dispatch. And after that we will define the maximum, minimum and maximum generation, and define the load power demand also, and the initial for each generation from where it started. In the economic dispatch, and after that we will use quadprog to calculate the economic dispatch dependent on the H and C and the load power minimum, maximum, initial power, and the option and type of optimization. And after that we get that value of power and the storage in the gbest, the value of power from each generation multiplied by the state of that generation. And after that we calculated the the accumulated fuel cost and the emission cost, and the fuel cost and the emission cost for 24 hours. And after that we start to display the power from each unit for 24 hours and the power from wind. As you see here, this is the generation from economic dispatch. And after that this is displayed here, and then we display also fuel costs, emission cost, and the startup cost and the total cost. And after that we start to plot, as you see here, plot the converging curve for this optimization SSA, and then we also plots for each generation unit, the generation in each hours. And after that we plot the cost in each hour and the emission of each hour, and then we end this the main function. In the next videos we'll explain the subtitle sub function in this program. This is the video to calculate, explain the sub function in the SSA function. The first function is the initial. This is, as you see here, the x we initialized the x by 1 for 24 hours for each generation, and after that we multiply the random and multiply by 1 for 24 hours for each generation divided by p, and this is random, and after that we compare between the STF that we calculated here and the random numbers and put it in the x as the initial states, and therefore the verify, as you see here, this is the function for minimum down correction, as you see here, and this is the reserve constraint correction if we need, and if this is for if you need to increase the power from generation, and or the commitment constraint correction. If you want to decrease the object function, we will concentrate it as the same of the results. The object function, we have input the state of each generation that will define as a unit commitment. So SSA will define the unit commitment, and after that the program is calculated the economic dispatch. So in the object function, the x, that mean the unit commitment states for each generation, and the number of generations, the number of times, the initial for the generation, minimum downtime, maximum power, and minimum power demand A and B and C for generation, and the startup hot and cold, anti-cold and T-off, and all the convergence factor of the emission also. So as explained in the first video, this is x, this is the states of each generation that defined the unit commitments. The SSA will define this x 0 or 1. So the 0 mean the unit is off, and the 1 is means the unit is on. And this is how do you say this is explained or defined as a unit commitment. This is a relation between SSA, as SSA will try to optimize this x, and after that all things is the same thing to calculate the economic dispatch. As we explained before, calculated the startup cost, and after that the f object is the sum of the startup cost, fuel cost, emission cost, all in the object function. This is dependent on the weight factors if we want. So as you see here, SSA will optimize the value of swarms. That swarms is, as you see here, if you run the program, we will define like this. This is one for 240 states, and this is dependent on the number of generation, because the number of generation is 10 and then 24 hours. So we have 240 states for each generation, and for the first hour, if you open the x, the first 10 state is for 10 generations for the first one, and the second 10 for 20. This is the second hour for each generation, the state of each generation, and so on for 24 hours. So the SSA is optimized the state of generation for each hours, and after that we calculated, as you see, calculated the emission cost and the fuel cost and economic dispatch, because when we defined, as you see here, we defined the value of x is the generic unit generation is on, so we calculate the emission and the fuel cost, if not will be 0. And after that, this is the unit, the unit which on is included in the economic dispatch and the off is excluded from economic dispatch. And after that we calculated the fuel cost and emission cost for each hours and sum it in the final of object function to calculate or final the total cost for 24 hours and the startup cost and the emission cost for 24 hours. And dependent on this, the values, the function SSA will try to minimize this all the variables, minimize the startup cost, to minimize the fuel cost and minimize the emission cost. This will be the final videos, and I hope you understand the video. So if you want to have any question, you may put it in the comment section and we will reply. And please like the video. Hopefully you enjoy this video. Thanks for watching.